you see the title here. Thank you very much, and big thank you to the organizers for making all this happen here, including the previous workshops and this one. It's an amazing meeting. I apologize for not having put the... Okay?
No.
No.
Is the red light on?
Yeah, red dot's on.
Okay. Just move it up higher.
Okay. So... Better? Yes, no? Okay. Yes. Okay. So, apologies for not having put an abstract. The only advantage was I could add some last-minute material. So, but the big topic is to use rough path techniques in SPDEs. And so let me get straight. So I should say this is joint work with my former PhD student Harald Oberhauser, my current postdoc Michael Caruana, and the new PhD student in Berlin, Joshua Diehl. And let me get straight to the outline here. So I'll talk a little bit about rough differential equations, rough path analysis. I'll give some reminders about viscosity theory, but I'll keep it short because yesterday we've seen a great lecture by a specialist in the field. Then we'll talk about the rough pathwise approach to SPDEs, and then I'll have one little note on backward stochastic differential equations driven by rough path. Good. The motivation for this is roughly given by two papers from the past. There's the seminal paper by Terry Lyons in '98, and I've tried to put it in 6 lines. So the one way to frame his result that requires little sort of notation, or as little as possible, I think, is the following. You consider a sequence of driving signals. So these are the set here. Let's see if that works. I'll take the stick. So these Z's here are driving signals, multidimensional, and you stick them in this ordinary differential equation, and subject to some assumptions on the vector fields, of course, for every n you pick up a solution. Now we will impose that this sequence here has a certain analytic property, namely we want it to be convergent in rough path sense, and for that I need to tell you what that means, and I will on the next slide. So just take it for now, it's Cauchy in some metric that we will talk about. Then the assertion is that these solutions here will converge to a limit, and this limit only depends on this rough limit bold set here, and it does not depend on the approximating sequence. So that's one way to state this limit theorem by Terry Lyons. I've put it here in a finite dimensional setting, but all the estimates that underlie this theory are dimension independent, and there's a perfectly good Banach theory of rough paths. Now, the other result that sort of inspired this present work was given in a series of papers by Lyons and Souganidis between '98 and 2003, and I've tried to present it in a way that points out the similarities. Again, you think of some sequence of driving signals, and again they are convergent, but now the convergence is in uniform norms, so we don't, we all know what that means. And they consider a sequence of approximating problems, namely the following parabolic PDEs understood in viscosity sense. So F, you can think of F as the Laplacian or something fully nonlinear, Bellman type. And here is some noise term. Now, as long as Zn is C1, then this is, this just amounts to some continuous dependence in time. And classical viscosity theory will tell you that, subject to some conditions on F and H, there's existence, uniqueness, comparison, everything you want. Now, the result there is these UNs, the solutions to these viscosity PDEs with some fixed initial data in book space, say, converges uniformly to some limit. And again, it only depends on this sort of limiting object, limiting driving signal Z, and it does not depend on how you approximate it. And the curious thing here is Z is only continuous, so there's no way you can compute Z dot. So there's something to be, understood here how this plays together. Now, back to rough differential equations. So again, this is the statement from the previous slide here, and I want to tell you a little bit about what these words mean here, rough path metric, etc. So the interpretation of that theorem is that this limiting object here satisfies some limiting differential equation, and you call it a rough differential equation. If you don't like this limit definition of what it means to be a solution to a rough differential equation, then reassure yourself there are intrinsic definitions that give a local description. So what are rough path metrics and what are rough paths? So the first example, just to fix ideas, if you stick with some Hölder exponent between 1/2 and 1, then you define the usual alpha Hölder metric here. So, this metric doesn't separate if these are, apart by constant, you won't see it in that metric. But since you're only looking at differential, you can assume without loss of generality all the driving signals start at 0. So it's a perfectly good metric, the alpha Hölder metric, if you want. And all the limits that you can cook up by looking at smooth or C1 path, all the possible limit points in that metric, so the completion of smooth paths in that metric is essentially, these are the alpha Hölder paths. So there's an epsilon lie here. If you take the closure, you get something separable. If you look at the alpha Hölder path, it's a not separable space, but epsilon close enough, okay? And these rough differential equations, these abstract rough differential equations, are just Young ODEs. That means you take this differential equation, write it in integral form, and the integral that appears on the right-hand side makes sense as a classical Young integral. So you're, in a classical setting in a sense. Maybe worth pointing out, Young ODEs, that's what they're called nowadays, were actually only considered by Terry Lyons in '94. He had the motivation then already to go further. So downside of this example is not applicable to Brownian motion. So interesting as it may be, doesn't apply to the usual stochastic differential equations. So the better example that's relevant for people in this audience, I hope, is that you stick with some alpha exponent between 1/3 and 1/2, and surely this applies to Brownian motion. Alpha anything less than 1/2 will do. And now you have to be a little bit smarter here. You still want the Hölder norm or the Hölder distance of the underlying path, but you take your smooth path or your C1 path and first build an object that's a little bit bigger. So here's just the increment of your path. This is zt minus zs, of course, for smooth path z. And here you look at the iterated integrals, right? And if you have ever seen or taught a course on numerics for SPDEs, the Milstein scheme, etc., you know why this term here is relevant or where it comes from. So you look at these iterated integrals and call this if you want, the second level increment or whatever you want to call it, and this is the one you put here. Okay. Observe there's a 2 alpha here, and if you think of Z being Lipschitz, which actually is the case here, then the scaling of this object would be like t minus s squared. The scaling of this would be like t minus s, and this 2 takes account of this scaling property. So even so, this is a perfectly well-defined story for a smooth path Z. You can define this thing and you can write down this metric. Now you ask yourself, what is the abstract completion? So the theorem of Terry Lyons would tell you that you have continuity in this metric here. So you want to look at the completion of this space of smooth driving signals with respect to that funny generalized Hölder metric. And maybe not too surprisingly, this completion can be completely understood. It's a rough path space. And the remarkable or the important thing to notice is it's not enough anymore to think of the driving signals as a path in RD. You have to allow for a little bit more room here. You have basically need space to put in what replaces the iterated integrals. So this is now a priori information that you need to be given, right? And then all objects of that type that satisfy these general Hölder conditions are, well, let's put it this way, the closure, the completion of C1 paths live in that space. There are some algebraic properties that persist. I'll say a word about them, but they won't be important for what follows. Namely, in a sense, this state space here is a little bit too big, because if you think about it, the symmetric part of this matrix here, just a consequence of the product rule, turns out to be just the 1/2 tensor square of the first level increment here. So in a sense, you can forget about the symmetric part of this, throw it away. It's redundant information given that you know the path increments themselves. And so this is in one-to-one correspondence with sort of this antisymmetric part A that has a neat interpretation as the area. And that's one of the few pictures I want to draw here. So if you think of D equals 2, and your path here is like this, and here you have time S and time T, then the simple application of Stokes' formula, or whatever name you have it for it, that so for a smooth path, this corresponds to the area you wipe out here. Okay. Now, this is one of my favorite examples here because it's the first non-trivial but simple example what a rough path is and what it does for you. So here's a rough path that looks completely trivial as a path, namely it does nothing, it just sits at the origin. But on the second level, something happens, namely you move in that direction t minus t. So this was what's written here. And then it's a little analysis exercise, quite fun actually, to prove that if you look at these approximations here, they converge to this rough path in this right alpha Helder metric. Alpha anything less than 1/2 will do. In fact, the way you prove it is you prove uniform convergence, which is cheap, and then you prove uniform 1/2 Helder bounds, and then interpolation gives you this in alpha for less 1/2. And what's the interpretation here? Well, basically you spin around the origin very quickly. So the radius is 1/n, but the speed is proportional to n square. And every time you run around, you cook up area proportional to 1/n square, but you do it n square times. So you see the area will not disappear. And this is exactly what you see up here. Okay. So if nothing else, you can take this abstract object, stick it in here, and this machinery gives you something, but you want to know what it is and does it have a meaning. And the meaning is the following. It models the effective behavior of the ODEs that are driven by these approximations here, and then do a little Taylor expansion on this differential equation. It's not hard to see that this rough differential equation here, or the solution to this rough differential equation, is precisely the solution to the ODE, where you look at the vector field given by the Lie bracket here of these two vector fields. So it models sort of the effective behavior of some highly oscillatory ODE system. Right, stochastic differential equations. The punchline is that this object here cannot be defined. So as soon as you have dimension 2 or higher, you can't define the iterate integrals with S. Riemann-Stieltjes integrals. We all know that. But you can use Ito integration or Stratonovich integration, and my little round here indicates Stratonovich integration. The reason I want to stick to Stratonovich here is that in the end we want to look at it as limits of ODEs, so Stratonovich is sort of canonical here. Now you can define this object here, and then it's an exercise in using Kolmogorov's theory or Garcia, Rodemich, Ramsey to show that with probability 1, this object here is an alpha Helder rough path for any alpha less than 1/2. The only reason I stick with greater 1/3 is if I want to be in the step 2 rough path setting, there's a theory for any sort of level of roughness, then you better take alpha greater than 1/3, otherwise you would need to include higher iterate integrals. But for Brown motion, it's cheap. You can get as close to 1/2 as you wish, so taking it greater than 1/3 is not a problem at all. What else? Any reasonable smooth approximation to Brown motion converges to be in rough path metric. In particular, piecewise linear approximations converge to rough path metric, and that already allows you to identify solutions to the rough differential equations driven by this Brownian rough path as Stratonovich solutions, because you remember the Wong-Sakai theorem, of course. There are other approximations. You can look at L2 approximations, so you pick So Cahoon and Löwe type, they will converge. You can look at the modifiers, they will converge. So everything that's reasonable will converge to the Brown and rough paths in this rough metric, and you get immediately limit theorems. But care is necessary. If you're unreasonable, and I don't want to call McShane unreasonable, but he cooked up some approximations to the Brownian path where you spin around sort of in a wicked way, and sure enough, you can cook up some extra area here, for instance, of this term here. And in that case, the effective behavior of the RDE would be the one that corresponds to a Stradonovich solution, and this one will manifest itself in an additional drift term that includes the Lie bracket. So it's not too surprising given the previous slide. So you have to be a little bit careful. So what's in for the probabilist here? Well, you have a truly pathwise theory now. So once and for all, you create Brownian motion and these iterated integrals, which are equivalent to Brownian motion at the Levy area. And then you work on a set of full measure forever. And you do all vector fields, all coefficients simultaneously, etc. There's a price to pay. There's some regularity in V, which goes beyond the Ito theory, 1 degree. But if you compare it with Stradonovich theory, then it's actually quite close. Construction of stochastic flows, well, this makes sense immediately for all y0 simultaneously. There's no, you don't have to do any modification business. Moreover, if you look at the solution flow to this RDE and you assume some regularity, and for the sake of giving some quantitative information here, 3 plus epsilon will do. So Lip here is in the sense of Stein, which means they are bounded vector fields. They have 3 derivatives, 3 bounded derivatives, and the last one is epsilon Halder. Under this assumption, you can see that, well, first, the flow itself, of course, exists. It's differentiable, and in fact, twice differentiable. And if you want more, then you just add more regularity here. And they all exist and depend continuously in Z, so a local uniform topology I want to put here. And also for the inverse of the flows, which is actually important in applications. And limit theorems for stochastic flows are, all follow from this continuous dependence in Z in rough path sense. So other advantages, if you have vector fields that are anticipating one way or another, no problem. You can go beyond Brownian motion and martingales. In fact, if you're interested in that, there's large classes of Gaussian processes and Markov processes fit in. And there are various applications of this continuity property. Perhaps the most convincing, or one of the nicest one, I think, is the support theorems of Struck-Varadan, which were so difficult to prove, but now they're very simple. And all these are plus. There's a little minus here. If you compare it to Ito theory, yes, it's true. You need 1 more degree of freedom, but it's not a problem of the theory. You get more information. You get robustness, uniformity. You work on a set of full measures, so you can actually show that all these the theory at its current stage is all the estimates are optimal. If you require less, the statements you get would not be true.
So if V is just global ellipses, can't do it?
See, V here is bounded. Now, in practice, if you have some a priori information of this, then you can localize and you get away with it. If it's just Lipschitz linear growth, if V is linear, you can do it, and that's actually very important that you can do it. But to be quite honest, if V is just Lipschitz, yes, it'd be nice to have it, and I can tell you later there's some work in progress, but it has not been any sort of obstacle in any sense up to now, at least not for my point of view. Now, this was my quick crash course on rough paths here, and now something that we have seen yesterday. So there's this viscosity theory, and you can think of F as the Laplacian here, or something much more general. In fact, let's think of F just a function of 5 variables here, and it should be continuous. That maybe some applications you want less, and you have to work extra. And the key property is it's weakly elliptic, which means there's some monotonicity here in the Hessian, which basically says you are not allowed to run the heat equation backwards, because if you do, then surely you won't have any stability. So under some technical conditions, that means TC here, you show that these equations have a unique solution. They solution exist, etc., etc. For initial data, so we look at the Cauchy problem. And you have more than just uniqueness. You have comparison. That's the key business in viscosity theory. So if U is a sub-solution in viscosity sense, and I'll say a word about that in a minute, and V is a super solution, and you have sort of matching initial data, then you already get the solution sort of satisfy this inequality for all times. So the meaning of U being a sub-solution in viscosity sense is that you try it out for test functions, and the test functions here are of the form so if this is your function U, and you look at the test function that touches it from above at some point, which here's t bar x bar, then the touching implies that all the first derivatives, all the first order derivatives are identical, and touching from above means that the Hessian of this test function dominates the Hessian of U, at least if U is smooth, which assume for this little discussion here that motivates it. And so if you use this weak ellipticity, then you pick up this inequality here. So again, the first order derivatives, partial t and d, they're identical at this point because of the touching, and here you have some inequality, and weak ellipticity tells you it goes in the right way. And so what you see is, if U is a classical subsolution, then you get another inequality, namely this one. And now forget about this here and make this a definition that's applicable to any continuous U. That's the definition of a viscosity subsolution, and you guess how you do it for a super solution. And amazingly enough, this definition plus some technical assumptions gives you a very complete and pleasant theory. Now, stability is a key aspect of viscosity theory. Namely, if you look at a family of sort of approximating problems, so f epsilon should go to f locally uniformly, and assume for a moment, this is sort of the tricky point here, assume you know some compactness about the U epsilon, so U epsilon goes to U also locally uniformly, then this limit here is a subsolution of the limiting equation, right? And the proof is very short, it's pleasant, and in particular if you compare it with the if you were to do classical PDE theory, a Friedman or so, if you want to show this, then somehow you have to look at the limit equation. You have to see that you can pass through a limit here. This involves derivatives and second derivatives of U epsilon, and somehow you have to check that they converge. Here you don't. So that's a very pleasant feature. Now, as I said, this assumption is sort of hard to check, or can be hard to check. So the following variation on the theme due to Biles Bertam in two papers, 87, 88, so got a very slick way around it. Namely, again, assume you have approximating problems. So U epsilon are subsolutions to these approximating problems given through f epsilon. Again, f epsilon converges to f locally uniformly. And now you replace this convergence just by locally uniform bounds. Okay? Then you get that a certain limit here. So the problem is you don't know that this U epsilon converges. But if they are bounded, then you can look at the lim sub and the lim inf. There's a similar story here. And actually, that's not quite enough. You have to look at these semi-relaxed limits. And I wrote precisely what it is down here. And then it's a theorem that this U bar is a subsolution of this limiting equation. Little care is needed because, in general, even if the U epsilons are all perfectly continuous, this semi-relaxed upper limit is only upper semi-continuous in general. So you have to revisit the theory a little bit and do it for upper and lower semi-continuous functions, which is not a problem, it turns out. Similar for super solutions. Now here's how you apply this, and this is precisely how we will apply it. Assume you have U epsilons that are actually solutions, not only subsolutions. So it means they're subsolutions and super solutions. Again, f epsilon goes to f locally uniformly. And if you know that this U epsilon are locally bounded, same assumption, and you know that comparison holds for the limiting equation, then U epsilon will converge locally uniformly to some limit U, and U will satisfy this limiting equation. In fact, it will be the unique solution to the limiting equation because comparison already implies that. Okay, so it's a little relaxation here. And if you want to prove, so like the classical application of this technique would be that you prove that the first order Hamilton-Jacobi equations, if you regularize it with epsilon Laplacian, you send epsilon to 0, singular perturbation problem. If you want to show that the limit is the viscosity solution that you have defined with your touching test functions, you use precisely this. And the proof is 5 lines. And the book of Fleming Sona is a very good source, but there are many others. Right. So the aim is a pathwise theory of fully nonlinear SPDEs of this form here. And as you've seen yesterday, we're sort of a long way away from it, but nonetheless, there's some good news. So here's again the theorem I cited in the very beginning. So for fixed initial data and convergent driving signals, uniformly convergent, you have these approximating problems here, and then the theorem of Lyons-Sogonidis tells you that these solutions, these UNs here, converge locally uniformly to a limit, and that limit only depends on sort of the limiting driving signal Z here. And the interpretation is you have sort of a pathwise theory of these, nonlinear stochastic differential equations, stochastic partial differential equations. Understood, there's no stochastic in here at all. It's a pathwise theory. So if you want to apply it to a stochastic setting, you take a continuous sample path of Brown in motion and you're in business. And at this stage, you should sort of wonder that this theorem looks much nicer than what you have in classical SDE theory, because it's certainly not true that in SDE theory, solutions depend continuously on the driving Brown motion. And this McShane example is, if you want, is the proof of that. So I'll return to that thought in a moment here, or let me do it immediately. So that's precisely the reason why the X dependence here is difficult. If you add X dependence, then it turns out the characteristic equations, right? So you just forget the F here and keep the first order part. That's a first order, differential equation, nonlinear, so local solutions, you know how to do them, a la Kunita. And it turns out in the X independent case, these stochastic characteristics equations also have some commuting structure a la Doss-Sussman, so you solve them directly. They depend, directly on the continuously in the path Z in uniform norm, and that's the reason it works. There's much more to it, but this is sort of the one aspect I want to point out here. Once you add X here, that's not true anymore. So there is, I guess if you want to know what the latest status here is, you need to talk to Takis. I understand that for Brown in motion, they can now use some large deviation arguments to make it work, but now it becomes really stochastic theory, and sort of you lose a little bit the pathwise flavor of it, but even so. We also consider a different class of equations where you don't have a gradient noise here, but just dependence, nonlinear dependence on U itself. So just to make sure, U where everything is evaluated at some X and T, right? H is just a function, or in fact a family of functions, because everything is multidimensional here, that depends on one real variable, that's U, X, T, right? We're not looking at operators or something fancy. So they also have a note on this type of equations, and the stability of the solutions that you pick up there, you should use rough paths. I mean, there's a stability result if Z converges in rough path sense. If you really want a pathwise theory, you probably put some commutating structure, and you probably don't want that. But if you add an X here, then the sort of characteristic equations just become classical, differential equations, stochastic or rough if you wish, where X figures as a parameter. So here the X dependence doesn't matter too much, whereas in the gradient case it makes a huge difference. Right, so to get started, the first thing we could do is look at linear dependence in the gradient. So that's a very pleasant case because the characteristics don't cross, so you can solve and invert them globally. But we wanted the X dependence, so we're, we sort of don't bother with the nonlinearity, which is very hard here, but at least we sneak in X dependence. And now there's a perfectly good pathwise theory, but actually it's rough pathwise, and it wouldn't be true pathwise. So if you have UN converges, well, let's start at the beginning. initial data is fixed here. Zn are smooth driving signals, and they are Cauchy rough path metric with rough path limit Z. Ignore the geometric here. Everything we're talking about, oops, are geometric rough paths. So there's, for those who know the terminology of the subject, I just call them rough paths here. So you know what that means because we talked about it in the very beginning. And then the statement is Un converges to U, and this limiting object only depends on the limiting rough path Z, and it doesn't depend on how you approximate this rough path Z. And the interpretation here is that you have a theory, a rough pathwise theory of this partial differential equation driven by this sort of rough term here where you have gradient dependence here. So if you want to apply it to stochastic setting, you have to construct your Brownian rough paths. We did it previously. You add the iterate integrals, so it's essentially Brown motion at Levy area, which is the right. So I already said that I don't want to fuss more about that. If you have x dependence here, then you need a rough path theory. Otherwise, skip f and you reduce it to some, you can solve it globally with characteristics and reduce it to the discussion of some SDE or RDE if you want, and there you know that you don't have a pathwise theory. So the proof here is simple. Namely, here are the approximating problems. I'm looking at the characteristic equations, if you wish, right? So forget the f. I just want to keep this term, and we solve it by the methods of characteristics. And that amounts to look at these differential equations here. And we know that the rough path convergence of these Zn's entails convergence of these solutions here to y, well, y solves this rough differential equation. And moreover, we know that this happens not only for fixed initial data, but this happens on the level of flows of diffeomorphisms. And let's call them psi n and psi. So now we do this change of coordinates that Takis explained yesterday. We rewrite it in new coordinates with the aim of getting rid of that noise term here. So in the SPDE language, you reduce a stochastic PDE to a random PDE, which is a classical trick used many times, and I don't know who was the first. So in this new coordinates, Vn solves a new equation that depends on n. The coefficients in there are a little bit, messed up, to use Takis' expression, but you can still handle them. And more importantly, what you see in the coefficients in there are sort of the derivatives, the second derivatives of the inverse flow, but we know that these converge. That implies that these Fn's converge locally uniformly to the F where the transformation you use is the rough flow. So that's one of the key observations here. Assuming local boundedness of Vn, we want to apply this Ball-Verdammt procedure, and this you usually get cheap, right? Formally, you need to make it an assumption here, this theorem, but in concrete assumptions, situations, you get this quite cheaply by some a priori bounds. So then, Ball-Verdammt procedure tells you you're in business here. If the UNs are viscosity solutions to these approximating but classical viscosity problems, then you will conclude that the Vn's converge to V locally uniformly, where V is the solution to the limiting problem. So in the new coordinate chart, it's a standard application of this stability story. Then you can unwrap the change of coordinates and define what you mean by a solution to the fully nonlinear PD with rough path noise here. Or if you're looking now for a good definition to frame your results, you can either say a solution to this equation is by definition one where the transformation of u, that means this here with n replaced by, so just ignore the n here. If given some u, you cook up this v here, psi is the rough flow here, and you define u to be a solution to a rough differential equation if the transformation v satisfies this equation. It's a perfectly good definition. You have existence, uniqueness, stability if you do that. Or you take some limit point definition as you wish. So you should emphasize that there's continuity built in here. So if u is the locally uniform, so u that you construct here, this solution to this rough viscosity PD if you want, is the locally uniform limit of the approximating problems. Moreover, the solution you cook up depends only on this rough path limit and not how you approximate it. And finally, the solution map here is book data and driving rough path is continuous, which topology, well, U here is just a point in, it's just in the book space, so book on Rn, so you put the topology of local uniform convergence. Z here lives in a rough path space, so that's a perfectly good metric space. And here again you put the local uniform topology on book space. So the take-home message of this is that the convergence properties of rough path theory, namely on the level of flows, and the stability properties of viscosity solution, they work hand in hand. Applications to SPDEs, again, rough path wise. So cook up your rough path and then off you go. Maybe a quick side remark. Everything is sort of heading towards a Stochastic theory, so there's no need here for stochastic parabolicity that you need in the E2 formulation, but that's an obvious remark. Right. Now, the work of Lians and Tsukanidis was sort of targeted to understand fully nonlinear equations, so let's go in the other direction for a moment and let's see what can we understand in a fully linear setting. And so let's look now at this equation here, and for instance the Sakai equation would fit that framework here, and in a general case when there's correlation between observations and sort of the noise terms in the filtering problem, there's a gradient term here, so the standard robustification trick doesn't work. So the general form is of this type here. So L is second order, so linear in the Hessian, linear in the gradient, linear in the U. Coefficients may depend on x and t, subject to regularity assumptions I don't want to go into. N here is similar, but just first order. Of course, you can't hope for second order here. And the result here is more or less the same, namely, you have stability of that PD in rough path sense. So, same story, if Z, the rough path Z is approximated by smooth paths, then the solutions of these approximating problems will converge locally uniformly to this object here. Okay, and again, you have the continuity. So, that's some aspect of, I mean, in a sense, ever since 98, rough path theory applies in a Banach setting, and you think of parabolic equations sort of as, as ODEs in a Banach space, and it's sort of tempting to ask, well, does this work for PDEs? And there were various obstacles, but so if you take this point of view, then it works. So why is this useful? Well, once you have this continuity property, it's really key for many applications. So if you want to prove some approximation theorems that you can check that these driving signals converge in rough path sense, then you're in for a limit theorem. If you want to prove a support theorem, you understand the support of the driving signal in rough path topology, which we do for many examples here, then you get a support theorem for the SPD here. Splitting methods can also be reduced to, or can be obtained using these continuity properties. Maximum principles can be obtained. I'm not saying that this will always give you the sharpest possible result. In fact, they won't, but it's a very appealing way of thinking it, of getting them. Moreover, if you want to identify this here, if you really want to say, well, this is something people have considered previously, if Z is the Brown rough path, then you naturally resort to the works of Yonji, Krylov, many others to use the approximation results for SPDEs, so Wong-Sakai type theorems for SPDEs, and that will tell you a priori that this rough PDE solution where you stick in the Brown rough path is actually sort of the Stochastic solution that people considered previously. So how much time do I have left? 10 minutes, okay, that's good. So let's quickly at the proof of this linear case, because I think it's interesting. I mean, what happens in the background is we solve the characteristic equations, right? But so to stay organized, you have to do it in a smart way, I think. So first, since this is linear, we sort of can break it apart and without loss of generality, write it as the gradient terms here, and then things that are just linear in U here, you could make some additive term here as well that doesn't change much. And so if we proceed similar as in the previous proof, namely we first get rid of the gradient term. So to that end you need the solution flow of this auxiliary differential equation. And if you do that, then this new variable or this new function w, which is the transformed u, satisfies a new equation where this one is gone, but this one sticks around. Unfortunately, or it's just a fact here, if you do a change of variables, this x here becomes a psi of tx. So to make sense of this integral now, you definitely need rough path theory, which if this term were not here and you just would deal with that directly, then you can cook up a pathwise theory, there's a robustification. But here, after the first change of variable, you have to make sense out of this. And while the linear structure helps you a little bit, although it's not essential, we'll talk about that. Namely, if you look at the corresponding solution flow that corresponds to this nonlinearity here, it has this form here, so you don't need to solve even a rough differential equation. You just consider the log of phi, and that now is a rough integral. So psi here, t, is obtained by this one. If this, whatever this is, becomes a rough path, and this here becomes rough, this has to be understood as a rough differential. So, but that's okay, we can understand it as a rough differential. And then you do one further change of variables, namely this outer transform, which is also known as the Dawes-Sussman transform. And after these two sort of intertwined changes of variables, you're left with a equation finally where all the noise is gone, and it's sort of put inside the coefficients involving various derivatives of these flows here. And if the L you start with is linear, then this double transform here remains also linear, so you preserve the structure here. If you do nonlinear stuff, then it's getting much more messy and you have to do more work. So let's look at some nonlinear example here. This is the prototype, the model equation, if you want, of a parabolic equation that has nonlinear noise. So here's the heat equation. We think of given initial data, I didn't write it down. And now the nurse here is nonlinear in U. No dependence on the gradient, possibly x dependence, and Z should be rough. So that means H again is a collection of H1 up to HD, and Z is somehow a limit of an RD valued driving signal, a path. Okay, so sort of a natural question to, if this were not here, you just put it in a standard rough path machinery, x is a parameter, and off you go. Now, this sort of had, tickled a lot of people in the community. So one thing you could do is to say, well, if this one is not here, I know what to do. If this one is not here, I also know what to do. So why don't you try some splitting and run the heat semigroup a little bit and solve a little bit the RD and just see if you get some compactness. We have not managed to do that, but something else works. So if you understand this in a rough path sense, then the splitting actually will follow. So maybe you can get it directly, I don't know. But this was considered recently by Gubinelli and Tindall, and then a follow-up paper with Sami Tindall's student, Dia. And they sort of did some different approach. So instead of turning this guy here, putting it inside the operator with some transformation, they tried to use the semigroup here and put it in here. So they had to reinvent rough path theory to be compatible with this, unbounded drift vector field, if you wish. And they can get uniqueness and local existence in some Sobolev spaces. What they cannot get, it seems, is global existence, because the vector fields they end up with are not not bounded. They don't fit. They don't satisfy the assumptions that you need for global existence in rough path theory. So there was a question here, and so I should add this equation for just a path Z, but not a rough path, was considered in one of the notes of Leon Souganidis. I mentioned that earlier, but let's see how we can do it in the present framework. So let me skip the x dependence. As I said, it doesn't add too much difficulty here. You perform this. There's a typo here. Should be called the outer transformation, but it's the Dawes-Sussman one. So consider the auxiliary rough differential equation here, and then make the same change of variables. So using the flow of this guy, the inverse flow, you define a new function here, v, depending on t and x, of course. And then it's also transformed equation, and this one in much greater for Laplacian replaced by general f appears in this note by Leon-Souvigny I mentioned here. And this sort of is for a PDE person, this is I guess an interesting equation here, because you have this quadratic nonlinearity, and they are sort of, you have to do a little bit work. What saves the day here is that for t small, if you think this is the flow here, the second derivative of the flow starts at 0, right? The first derivative, the flow starts at the identity. So as t gets small, this guy goes nicely to 0. So for every epsilon, we can find a small enough time horizon where this one gets small. And then actually digging a little bit in literature, we had at least 2 sources with different level of detail where this is handled, and there's a paper in the Annals of Probability 2000 by Kobylanski, actually in the context of backward stochastic differential equations, where a comparison theorem more or less applicable to this situation appears explicitly, and it's written out in complete detail. There's also this note by Leon-Souvigny I mentioned, where it's sort of, hinted, or somewhat less detail, but the same conclusion. So you have to do it at small intervals. That means you carry out the procedure we had on small intervals 0h. You get this, you understand this on small intervals, but then you do a chaining argument. The h here doesn't depend on anything if uniform estimates, and so you get global existence here. So by the way, you also get this continuity sort of through, and if you now want a splitting result and say, well, let me understand this by running this one, and then letting the time step go to 0, it will follow from this one. So I know rates, or at least you have to do more work, but you actually see then afterwards that this you can also get it from a splitting approach. Right. I don't know how much people in this audience know and are interested in BSDEs, but somehow if you look at semi-linear, so if z is smooth, this is sort of a semi-linear parabolic partial differential equation, and now I want to write it as terminal value problem. Just that's why I have a plus here. Just change t to big T minus t, and that will do. And that can be related to the following Markovian BSD, namely minus dy equals h of x is a diffusion process associated to L if L is a Laplacian and its Brownian motion started at xs. Here is this little z, the driving signal. If you assume smooth, then no problem. And here is sort of morally, so that the link is that if you look at that guy at time s, then this corresponds to u at xs, and z is essentially the gradient multiplied with the diffusion coefficients. Right. I'll be done in 1 minute. Okay, good. So there's a work in progress. It's complete, but we have to write it up nicely. If you now look at the BSDs in a non-Markovian setting, which is sort of the natural thing to do once you identify the setup here, then you can ask the same question here. What happens if these sets here, what happens when they get rough, right? When z equals zn converges to some rough parts of z. And now there are stability properties for BSDEs in this paper by Kobylanski I mentioned, and it sort of mimics a little bit this Bowles-Bertam setting. And if you apply them in a correct way, so again you have to transform the BSD, and the resulting BSD will be what's known as a quadratic BSD. There's been a huge literature in the meantime because of some applications in finance. And if you massage these stability results by Kobylanski a little bit, they apply to this framework, and then you see compactness of these approximations here, and in particular what you can give meaning to this rough BSD, where now here's a rough driver here. So I believe there has been some work where z has been a fractional Brownian motion, and it relates to this backward doubly stochastic differential equations studied by Bardou Beng in '94. So this is some nice spin-off of this, I think. Okay, that's it. Thank you.
The next speaker can set up the talk while we take questions. So, are there questions?
Okay. Yeah.
Can you do any problems where the noise is not in RD, but D is infinite dimensional?
We have not tried yet. I mean, if you have to understand these flows. If you let, if the decay of the coefficient is sufficiently fast that it makes sense when d runs to infinity, I would believe you can do something, but it will be highly colored.
Can we go back to 18?
18? This one?
Yeah, that's right.
Yeah.
So in there, where did the rough parts actually come in? They come, is it just for the flow? Or
Yes, so here's the rough path.
So you use the rough parts to get the flow.
That's
And
right.
you know the flow depends, it's a sort of pathwise thing, and then the rest follows from
Exactly. So again, all these phi here and the derivatives, everything depends nicely on z in the rough path metric. So now I can play the same game subject to having comparison, right? So the same arguments work provided you have comparison for the limiting equation. And that's actually tricky in this case because of the quadratic nonlinearity.
Does this explode, the equation?
Pardon?
The random equation, does it explode in time?
Which one?
The random equation.
The second one.
So
The second equation.
this one.
Yeah.
Um,
You have the gradient square and have something in front.
where if I restrict myself for small enough time intervals, in a sense I don't care. I can do it on small intervals and then I use a chaining.
It won't explode. If you start with bounded initial data, it doesn't explode. They are global in time solutions.
Bounded initial data, not L2.
Excuse me?
For bounded initial data.
Bounded initial data, even for linearly growing initial data, you have to put quadratically growing initial data.
Is
to
it
have
true
phi.
for L2? L2?
The theory is not an L2 theory, it's an L infinity theory.
I would like to see it in Hilbert space.
I think we will have to break because we have already the program.
Oh, thanks for your interest.
So we